All right, one more thing regarding the nature of these waves before we go into the Schrodinger equation is that the wave itself, although it's related to the speed, they had a really big argument about what kind of a wave is it. Well, it's a matter wave, but I mean, is it a transverse wave? Is it a compression wave? Is it a traveling wave? You know, so we have different kinds of waves that we've been looking at in physics. We've looked at the mechanical waves, those like string waves or sound waves or those kind of things. We have electromagnetic waves, and they're a little different because they can travel through a vacuum. They don't require a medium which to travel. But the matter waves are even weirder and stranger. They have the properties of waves, but they're waves of probability. And so the interpretation of the wave function is that it's just a way of determining how likely it is on a given measurement to find the electron in a certain location. So if we go back to, say, our electron in the particle in a box, and the electron is going back and forth like this, just bouncing back and forth classically, quantum mechanically, what we're seeing is that the wave has a higher amplitude in the middle. And when you square that, it turns out that psi squared is the probability, or related to the probability of finding the electron at a certain location. And this is called the Born interpretation. That these are waves of probability, really weird waves. More specifically, in terms of units, psi squared can be thought of as the probability per unit length. Of finding the particle in a certain region of space. And so if psi 1 here, let's say were the wave function for a sine wave that had a wavelength that was equal to double the length of the box, then psi 1 squared would be a little more peaked function. So this would be proportional to the sine of kx. Okay, and here we're assuming that we're looking at a certain time because it's a standing wave, the time dependence, although when we looked at waves that modulated through time like this, we're basically looking at a steady state solution for an electron. And so one that doesn't evolve with time is one that just has that kind of a fixed sine structure. So this would look like the sine squared of kx. And that would be our probability per unit length. And so the interpretation of this then is that we're most likely to find it at x equals L over 2. So in other words, if we make a large number of measurements, we're going to find it most often here. We're going to find it less often here, and then we'll never find it here. The area under the curve to just the 0 point, let's say. Okay. And you'll find it once in a while at x equals L over 20, but not that often. Most often we'll find it at x equals L over 2. Very rarely will we find it at x equals 0.95 L. Okay, but more likely to find it in the middle. So upon taking a large number of measurements of this system, what we find is it's very much like rolling dice. Okay, if you roll dice, let's say you've got 2 dice, and you roll them. Here's the total And here, we'll, let's have the total number of rolls. For a given number. And so this is the sum of the two numbers. Okay, so the one that you're most likely to find then is a 7. Okay, because a 7 you can get from a 4 and a 3 and a 4, a 5 and a 2, a 2 and a 5, a 1 and a 6, 6 and a 1. But snake eyes, that would be here too. You only have one way to get that, that's double ones. And over here, at 12, that's the maximum roll you can get from 2 dice. There's only one way of doing that too, a 6 and a 6. But a 6 here you can get as a 5 and a 1 and a 5, a 3 and a 3, a 4 and a 2 and a 4, like that. But not as many ways of getting it. So we can see that this thing, and we can do that with all these other numbers as well, we find that the maximum probability is at 7. And so 7 corresponds over here to the maximum number of times that we'd find an electron if we made a large number of measurements of the electron in this box. We would find it at all of these different possible locations, but with a probability that is similar to the kind of a normal probability distribution that we would have here for the dice. Although this would be a sine-squared function, and this normal distribution is not a sine-squared function, but I mean they look kind of similar. If we're not worried about the math, we can see that conceptually this gives us the same kind of an idea. And so this is a weird concept then to wrap your minds around, is that the electron is just a certain tendency to exist in different locations and only becomes an electron at a certain location upon measurement. But what this wave function gives us is the potential or the probability distribution of finding the electron. Just like I can't tell you what dice you're going to roll, but I can tell you what the probability distribution is for a large number of rolls, what that's going to look like. And the same thing is true here. So in a sense, we're affecting the reality by the act of measurement. And the measurement then causes it to become a particle. Okay, so is there any experimental verification for that? Or is that just some wild speculation? Well, it turns out that there is. If we take a double slit device, this, by the way, is how de Broglie, or de Broglie, that's the way his name is really pronounced in French, how he got his Nobel Prize for that PhD thesis that I told you about before, where remember Einstein came in and checked that all out and said, yeah, he's going to get the Nobel Prize for this. And so not only did he get his PhD, but he won a Nobel Prize. Good deal. And so in 1929, after he had published his thesis, what they discovered is that if you take a beam of electrons and shine them through a double slit apparatus, we get the same kind of interference pattern that you get for photons. So in other words, by sending a beam of electrons through this double slit that has a separation distance d, what was found is that the waves that travel through each slit can be considered to be like point sources, and in some locations they add together to produce constructive interference, and in other places they add together to produce destructive interference, just like with photons. Okay? And so what this is basically telling us then is that the electron is going through both slits at the same time, interfering with itself and producing either constructive or destructive interference. This is our interference pattern. And so here then we have constructive interference. Okay, so that's given by sine theta equals m lambda over d. And then in other places we have destructive, where sine theta equals m plus 1/2 lambda over d. And so the strange conclusion here is that the electron must be going through both slits and then interfering with itself to produce either constructive or destructive interference. But if you just let one electron go through, maybe it lands here. If you let another electron go through, maybe it lands here. Or maybe it lands there. But it never lands here. It never lands there. And so this is telling us then that the electron is in multiple positions at the same time and is either constructively or destructively interfering with itself. And then they said, okay, well, this pattern then is a pattern of an ensemble of many, many electrons that are going through and have a certain probability of landing in certain locations. So the places where the electron has a higher probability of landing, say here and there, would correspond to here and there, would correspond to individual measurements that are being made. And so those measurements then are associated then with this constructive and destructive interference pattern. And so a lot of people are saying then, well, okay, if that's true, then I should be able to measure and pin down which slit the electron goes through with a measuring device. And so this is with no attempt made to measure which slit the electron goes through. But then they put a measuring device in there. They said, well, I can't be going through both slits at the same time, so I'm going to figure out which slit it's going through. And so you put a measuring device by one slit. And then what they found is that the electrons only went through in this location, or they went through in this location and just made two large splats on the screen, as would be associated with a particle that has a definite trajectory and is moving through either one slit or the other. So just the act of having the measuring device there caused the electron half the time to go through this slit and to make just one bright spot on the screen. Okay, and so in other words, adding the measuring device destroys the interference pattern. And so in other words then, by measuring which slit the electron goes through, what you've done then is you, by measuring it, you've turned it into something that has particle properties. So here, quote, extracted the particle properties of the electron. And so they go, okay, well, if it's going to make a pattern like this, over here, what if I put the measuring device all the way out here? And you go, well, surely the wave must have already formed by that point. Can't retroactively change its mind. And so they're trying to sneak up on the electron and uncover the strangeness of this pattern. But it turns out that it didn't matter where the measuring device was placed. It always destroyed the interference pattern, even if it was almost to the screen. And you'd think the waves were almost just ready to interfere right there. Even by putting it there, it just retroactively determined which slit the electron went through, and then it started following this pattern. So this is regardless of the location of the measuring device. And so the conclusion of this experiment then is that it's the act of measurement that causes the particle to take on particle-like properties. And so some people have called this the collapse of the wave function. So somehow then this act of measurement has turned it from a wave that has these wave-like properties into something that just has the regular particle-like properties that we're more comfortable with. And so then it got into a big discussion as to, well, is this consciousness that's doing this? Have the yogi's been right for thousands of years, and that we're all connected, and that we create our reality by the way that we see it, and that this act of consciousness, it requires humans. Some people started saying, well, then it must be our human consciousness that's causing the particles to collapse. And so if there weren't any humans in the universe, then the wave function would never collapse. And so those kinds of conclusions, in my mind, go way too far. And we've seen examples of where humans tend to want to put themselves in a position of exaggerated importance multiple times in the history of the Earth. And the Greeks wanted to make the Earth the center of the universe. And here, this is just kind of, in my mind, another aspect of us interpreting the data in a way that gives us a position of exaggerated importance. So I don't believe that, but I do believe that there's something about the act of measurement that affects the information content of the system. And it's that information content that is affected by making a measurement. But it doesn't have to be a human making the measurement. It could be any potential information that is extracted by, say, the electron colliding with other atoms. Or it doesn't have to be a human experiment at all. It could just be normal interactions of the electron with the environment that produce this, what we could call it as information contamination, that prevents the wave-like properties from manifesting and allowing these particle-like properties to persist. Okay, and so I'm going to stop this here so we can just think about these concepts a little bit, but try to keep all of this in mind as we start to develop the Schrodinger equation in the next lecture.